Hello everyone, Goran will be presenting us the EMI EMC pre-compliance presentation. Thank you.
So hi to all, and thank you for attending my presentation. I will talk a little bit about the EMI EMC and some stuff I am working lately. So about me you will hear in the next talk tomorrow, but I am not an RF expert. I don't know much stuff about RF, and I'm just experimenting. So what took me to this experiment was that I'm always doing some hardwares. So I am having an open source hardware company, and I'm always doing the hardware, and I always need a way to like test that hardware and make it compliant at the end. So I asked the NLNet, because they are really good partners, if they can like finance me to find a way how can we measure those devices at home and make that process of compliance little bit less expensive. So what is actually EMC? So it's like electromagnetic compatibility. So every device will emit some noise, and there is like strict rules that you need to follow to actually comply with those rules. And if you pass those rules, you can get certificate, and you can, like, those are CE marks, and you can get on the market. If you don't have those, if you cannot comply with those rules, you cannot have boards on the market. Also, like electromagnetic interference. So it's it is interference. So when your device is like broadcasting, it will interfere with other devices, or the other devices will interfere with you. So you need to also have like compliance with that. So the way the things work is that you usually have a device, and you need to like do some pre-compliance, at least that you don't need to pay a lot to a company that will do a compliance test. So you usually do pre-compliance at home, but at the end you can actually do a complete compliance test at home, and you can like sign the papers that you are compliant. But if they catch you that you didn't measure your device and that your device is not compliant, you will pay a big fee. So that's like you cannot just sign, you need to do the measurements. So the prices of like getting the CE certificates are really like they have a really big range, and they start like on few thousand euro. But if you have like AC device and that has maybe the Wi-Fi or something, it will be like quite expensive. And if each time you are actually following the compliance, you will need to redo the boards, you will need to redo the testing, and like each hour in the chamber is cost in Croatia is like around 300 euros. So it's really, really expensive. So how can we make these things bearable? So first thing you need to know is that you can do maximum, you need to do a maximum when you are actually designing a boards. So that is the main goal, is to try to follow all the rules you can and make the board perfect as much as you can. So there are really good guides on the design guides for the boards, and you make sure that you follow those rules, because they are quite important. And when you do a mistake, it will cost you at the end. So it is best if you can follow those good practice guides. One of the important things that people are like missing are the return currents, and you need to always at least visualize on your board how your lines will be connected and where the back current will actually go. It will flow under the line, and it will try to find the easiest path. So it will try to find the way on the ground that is like shortest way to the signal. So you need to follow those, because if you make mistakes like that, you will have like crosstalks and you will emit more than you want. So that is and like maybe second important part is like how you set up like board stack up. So I am like, when I am doing the board, even the simplest board, I am doing like a 4-layer board. So the importance of like doing it in 4 layers. So if you have like 2-layer board and one is ground plane and one is the signal, when you have like low speed signals, that will not be super important. But if you have like high speed signal, it will be quite important, because the distance on the first layer and the last layer will be quite big. But if you use a 4-layer board, then the distance between the first layer and the second layer, it will be much lower. So I usually use 4-layer boards, and when I do the stack up, so I usually use a signal plane and then the complete ground plane. So the signal can always have like a ground beneath the signal. I also like sometimes when I do boards, so I use the power lanes on the top or bottom layer, because if you use like one layer in the middle that is power, you need to be careful, because that layer also like needs to signals on like bottom layer needs to like have ground beneath them, so that signal can have good return path. And yeah, so I already told you about like pre-compliance and do it yourself. So you can actually do it on cheap at your home, but there are some things that will be like tricky to do. The most tricky part is actually to isolate the external noise from the surrounding. And the second tricky part is to be exact. So you will, for now, I am also don't have like exact numbers, so I can only differentiate like device that is broadcasting a lot or less, and I can like say, okay, I am somewhere that I need to fix this stuff, or I can like bring it to the company that is doing the compliance test. So usually it is like a bit more expensive version is that you have like a normal signal analyzer, so it will like and like some special probes that are quite like around maybe the analyzer is around like 500 euros, and probes can be also like 500 euros. So usually it is done like that, but you can also like search for the open hardware and do it on the cheaper way. So currently there is existence of like tiny SA signal analyzer, and it's I usually use it this is like light VNA, but there is like the same thing is I have it on this on the table. There is also like tiny SA that can connect to a probe that are like just bare PCBs, so like this. So it is like, this is one from the guy that did like open source probes. So I started with those probes, and you can also get a little bit more of equipment. So you will need like amplifiers, you will need lots of connectors, you will need it will be good if you have like at least 2 tiny SAs, because you can then use one to send the signal and second one to receive the signals. You can then measure what is done with the signal, so if it's lost or what happens with the signal, or if you have antenna, if it's like, or and amplifier, how much is amplified. You will also need the attenuator, because with the attenuator you can like lower the signal down, so if you amplify it too much, so it can damage your equipment. So with although those equipment that is not expensive, there is no big protection in the like in inputs, so you will need to be careful what you are connecting to it. So when you have that tiny assay and probes, usually how they do it in the industry, there are multiple ways, but one of the way how they do it in the industry, they have like robots that is like scanning the whole board with the probe. So just passing around the board and finding the source of the noise. So I was trying to figure out how to do it. So first I did it with the hand. So you can just put a device to aggregate all the noise, and you can just pass around the board and like search for the area that is broadcast, or you can just pass through board and do a complete like board scan. But when you see that machine, actually you can do it at home on like a really cheap level. So you probably have 3D printer or something, so it's really easy to hook up the probe to the printer and let the printer move the probe. So you can have like scan of the complete board really easily. So in this case, I have used so I didn't design the probe holder, but I have found the probe holder I have found the holder for the camera. So usually Prusa's have like cameras to check if everything is okay. So one guy designed the holder for the camera. So I just used that one and just put the hole inside so I can put the probe and do the scanning. I can probably now run actually how it's working. So I'm just moving I actually in this case I was like I just put lots of actually samples for the printer to print, and I disabled the filament, so filament is not going out, and the printer is just moving. Okay, so let me get back to it. And like here are the results of the traces. So I did a few scans. So first I wanted to check if the open source probes are like good enough for us to do the measurements with them. And actually it seems that they are really good. Like you can buy. I have like more expensive probes. I use the one that are like a bit more, I don't have the picture here, they are like a bit more expensive. I used ones like that I bought from AliExpress, and I used this open source one. So, and here is like, if you see those traces, it is not quite visible how traces are, because on Tiny SA it's really, on the screen is small, and I had a problem like to read what is the what probe is better and what is not. So I actually contacted the NVOX, and in combination with them, so they have really nice tool for the like GUI creation, and it can do many things. But I used it for to design actually the graph that will like pull the information from the Tiny SA and show it on the screen. So it is barely like no code, low code thing. So you just have modules, you just push modules inside, and you get the project. And after that, like I used that for some time, and NVOX contacted me back. So they actually added, because this program it's used also for controlling the different types of instruments, so oscilloscope, spectrum analyzers, and whatever you have, like it's using like Skippy and like Serial or whatever. And they actually used my dashboard to add Tiny SA as an instrument. So now you can use it like any other instrument. So you can ask like what is the frequency, what is the current like noise and stuff. And after I had like that simple GUI, I had it like much more better visibility, so I can like check how probes are like compared with each other. And what I have figured out that we can use open source probes for actually things that are inside of some range like 30 megahertz to 1 gigahertz, it is fine. So there is no big difference between quite expensive probe and this one for like $1. Probably there is some difference, but you actually don't need it at home. So, what about the chamber? So you will always have like that noise that is coming from outside. So even with the probes, you will catch the noise from outside, and like industrial chambers are really expensive. Usually there are some like rules. So with the probes, you're actually measuring the near field. So, but on the tests, real tests, you need to measure the far field. So far field is at least like 1 meter, but they usually do it on like 3 meters. So you will, if you want like that far field, you will need the distance. But at home, we actually maybe don't need the distance. We just want to know if device can like be around the passing. So we will probably maybe never be capable of deciding if this device is 100%, but if we have certain certainty that it will pass, it will be good. So for the first try, I actually went all around the house and I put the tiny SA with the antenna inside of any device that I have found that is like boxy. So I have just put it inside, and I have found out that the oven is not super super closed, even like fridge is not super closed, but so you can move the device around and find what is like best way to block the noise. So I actually put the tiny SA in the microwave and find out that it is blocking enough of the signal. So I just went to the trash and just took one microwave oven and repurpose it to like a small chamber. I also tried to. I was also like searching for did anyone did it before, and there is like one guy that did all the like how you can like even partially calibrate the oven. So you can have like two antennas. One is like sending antenna. Second one is like receiving antenna, and with that signal you can actually somehow calibrate the chamber. Also, the slide I will on light slide you will see where those my slides are, and you can like use those news on my website. So you can there is like lots of write up on this. I'm just using few pictures and a little bit of talk, but there is really lots of write up on how I did it and what is like behind it. Okay, so what is when you have like when you measure the device in some chamber and you don't know actually what is the strength of the signal, you will never get the like exact numbers. So how can you decide if device is good or it is not good? So I have searched for the like device that is like noisy but not super noisy, that is not passing the EMC, and I have found that actually Raspberry Pi 1, it's edgy device. So when you measure the Raspberry Pi device, it will be on the edge of the passing. So sometimes people are reporting that Raspberry Pi 1 is not passing, and sometimes that is passing but is really close to the line. So actually ideal would be that we design the device that would have like that line of passing, not passing, and then you can just compare your device, your measurements of your device with the, like for example, Raspberry Pi. So I actually did that for my ULX2S and with code that is running. Actually, the most noisy part on the boards, those simple boards, are like SD-RAM. That is really crazy. So when you like put the SD-RAM into work, it will be all over the place. So like my board is almost does almost nothing if SD-RAM is not used. So I have used this PAVS 2. It's some like gaming system that is using SD-RAM, and when you start this, it is like doing crazy things. But with the actually microwave, the problem is actually the reflection. So first it is okay the size, but microwave oven is actually constructed to reflect any signal like to the source. So it's really hard to isolate the reflection. So whatever you put, any signal that is like broadcast, it will be quite easily reflected to your antenna. So that's not actually the perfect thing. So I have searched for the materials and what we actually need. So okay, we can isolate the chamber, but we need some material that is like in the big chamber. They have those like small pyramids that are actually absorbers. So we need to find some material that is absorbing at least some of the reflections. So at one data sheet of the material, I have the part number of material that I am using later. So it is shown how how this thing is measured. So how can we measure how much material is actually blocking the thing? So, and I have tried it with the hands to put the two probes in. They need to have they need to be separated at certain distance. So I have tried to with the hand, but it was too complex. So I actually designed the holder for the probes. So now I have I wanted one probe and second probe, and that I can put the material inside. And so this is my probe holder tester. So now I can put any material that I can find in the house, and I just put the material in, and I see I measure how much it is blocky. Yeah. So what I have found that there are I tested many materials. So I have found that this foil is okay. So but we still need to measure it. Maybe I don't have I didn't have at that time good amplifier, so maybe we need to do it. I have bring all the equipment here at BalCCon, so we can experiment outside, and we can measure different types of material, and we can maybe someone also has some equipment, so we can have real and good measurements. But the interesting thing is that actually the normal foil is really blocky, and if you have a foil tape, if you tape something with the foil tape, it is quite okay to have for do-it-yourself things. It will be okay. You will have also reflections, but you will not have these absorbing materials, but foil is really good. So I decided actually to combine the foil and this special material. I have also found that not all reflective materials are actually blocking. So there are different types of foil. For example, I was thinking it was really cool because so for the cake there is when you have a cake, there is one really cool thin thing what you are cake carrier or whatever it's called. So that was perfect for laser cutting. So I was thinking, oh, this is super cool. It is reflective. It will be aluminum, and it is called aluminum something. But when you put that in, you don't get any it just the signal just passes. So it's not everything that is reflective is actually blocking. But now we can test it. So, and after that, I actually wanted to test the foil. So I designed the small box that is actually designed in the OpenSCAD. So it's super simple box that has parts of I can put two antennas. I can also put the transmitting antenna and the receiving antenna, and I cover it with this is on the top bottom left side that is cut from that cake foil. But yeah, that later I didn't actually. Later I understood that it is not so blocky, so I used the tape and I taped the whole thing up. So, and it is really easy. You just tape it up and you just press them, on. So at the end of this chamber, I had I would say solid chamber that is that I can put the device inside and I can do the measurements. So I think I have yeah, the new video. I also So when I have talked with one guy from my makerspace, so Emard, he had other ideas. What can we do? That will go on with the next chamber. But we wanted to do it like easy, like closing and easy opening. So, and for that, using magnets is really cool because you can just like push the magnets and the thing will close. So you can see the signal, and now there is no signal. There is little bit of signal on 89 megahertz. That's the FM radio. So. Yeah, this is with actually with the amplifier I had at that time. It is not super good amplifier, but it is visible that you can actually isolate outside noise. You can get decent results with isolating outside noise. And these are actually the measurements of the different types of the chamber. So I have like yellow one is like microwave, the purple one is actually the open box, and you have like you will not see the difference with the red one and the green one. It is small difference, but that is the aluminum foil and this aluminum plus special foil. But yeah, it is. You see here how signal is quite blocked from outside, so it is like usable. When you want to like somehow calibrate or see how your box will do, you can use like two tiny SA. So you can set one to like minus 40 dBm. That will be the sending device. On the other side, you will have the same device that is receiving, and you can like push the signal on one side and check on the other, and you can compare if outside signal is maybe bigger than the thing you will measure inside of the box. So on the third picture, so I have actually the problem with my router that is near. So I would not be comfortable with measuring the 2.4 gigahertz because the signal from outside will go into the box, so I will not know the results. But on the other hand, from like 1 gigahertz to 2 gigahertz, I'm certain that none of the device will pass because I have like flat line from outside, and also from like 100 megahertz to avoid this FM that is really strong, I would be comfortable to measure device inside this box. So when I have talked with the guy from my makerspace, Emard, so how can we like do it maybe better? So how can we do it better than that box? And does he has maybe some other ideas? We search around and find that there are like those like triangle shapes measuring boxes that are also like quite expensive. So he had one idea that he loves pyramids and all those things, and he actually loves all those old tools, so like nets, but now it's like XNets 2C. So at one point I just got like results so that we can build a pyramid, and that pyramid is really cool shape. So, and that those measurements, I don't know what they represent, but that those measurements are like showing that pyramid will be good for that. And he explained me in a way that if you put the like source of light in the pyramid, and if you push it on the like any side of the pyramid, the light will like it will have lots of reflections until it reaches the top where the actually antenna will be. So that is like that is the idea of the concept. So if we put any signal in the middle, we will not get so much of so we will have lots of reflections that will be like absorbed, and those reflections will be hardly reach the antenna. So we will, in theory, had good results on catching just the emissions, not the reflections. So the pyramid is also like easy to assemble. So it's much easier than like like the box, and we also like combined these magnetic things on the pyramid, because we want like you never have like enough space in your like service, so you just want to like disassemble your box and move it somewhere on the shelf, and when you want to use it, you just want to assemble it as quickly as you can. So that's also like plus side on the pyramid. So after some time, he just pushed me the OpenSCAD designs for the like pyramid, the PCB holder, and actually antenna holders that are. He had a like opinion that we can just use actually the wire on the middle of the peak. So, and that wire should be like around 10 centimeters, but we can like do the measurements and check if this will be okay. So I just used my laser, cutted everything, and 3D printer to print those antenna holders, and use that special foil. He even sent me the like PDF how to cut those foils, because foil is like A4 format, and you need to cut it on the like pyramid shape, and you need to put like two A4, then to cut it at some like V to get actually use everything. So we use just I think three foils for the whole pyramid. So it is also actually cheaper to do it with the pyramid than with the box. And I also placed the magnets, and you will see later I have like those. So when I did the tests, the signal did pass inside, so you need to cover the edges. So I designed like super simple like edge cover, so I can just throw it there and it will like stick and have it, and we can cover the edges. And this is actually how this pyramid looks assembled. We started with the like bigger antenna, so that we can see more of the signals, because when you cut the antenna, like when you have the shorter antenna, if you don't have the good amplifier, then you will not see any signal. But we also knew at the start that wire may not be the perfect antenna for this pyramid, but we wanted to try it like this. So I have just in the quiet environment, so I have like one like basement, and I tested if the signal is like amplified signal. So this is with amplifier. So if I will get the external noise, and in this basement I didn't get actually from this is from 30 megahertz to 3 gigahertz, I didn't get any noise, so it's quite okay to, so the signal in the pyramid is okay, it is not going inside. And after that, when we discovered that that antenna will not pick up as much as signal as we want, so we have the idea that we need to check with some kind of like ball or some kind of like flat antenna to pick up actually more signal from the device, as we don't want like to amplify too much so that we don't pick up any external noise. So I recently, like a week ago, I pushed the design to GLC PCB, so I got the antenna, but I also didn't do the measurement, so we can do it outside and check if this will work. So antenna design looks like this. The flower is just my idea to have it somehow, like to beautify it a little bit. But it is just like a circle that is like have like bigger surface that can receive more signals. And he also told me something, that it is best to like, I don't know how it's like, to cut this like a pizza, so that we break circle impedance. I don't know what that should mean, but yeah, that's his thought. So I just cut this antenna like a pizza. So we will see if this will actually work. Also, when I was experimenting, there was other projects financed by the NLNet, and the guy that is doing like he's doing some wireless, he's doing some research on the wireless device, and he actually wanted to block the noise from inside to outside, and he find out that it is good to use this Titan RF material to cover the chamber with this like Faraday fabric. So I also bought that one, and it is really dumping the signal down, but we still need to measure it. So when I measure it with my equipment, I get like blockage, but we will need to measure it here to see how much blocky it is when we do more amplification. Yeah, and these are like pyramid tests in the like noisy environment. So when the Wi-Fi and everything is on, so it is still, so you can see that there is still like little bit of the signal on the like this bluish here. It is getting into, but I was just using Titan RF, so I just put it like throw it on the top, and you need to be aware that everything that is going outside of the box can also be like antenna for in the box. So if you have like any cable outside, it can also like signal can pass to the cable and then inside of the box. So even if the box is really don't let the signal in, everything can get it can get inside with the like power supply or with the like bad cable or something. But in any case, yeah, it is showing that usage of Titan RF is really blocking. It's adding it's adding quite a lot of blockage to a signal. And that's actually it. So I will now show you how to assemble a pyramid, but I need to do it like slowly so that guys can put the camera on the pyramid. And yeah, so you can actually ask questions. If someone has a question, please ask, and I will try to, with my knowledge, I will try to respond to you. And later when they record this pyramid assembly, you can get closer and to see what else I have, so, and what I talked about. So questions? Okay, so the idea was like that the assembly must be like quite easy. So when I actually the magnet, so that's it. That's how it works. And it's sorry. So it's really easy to assemble. It's easy then to like reopen the box to put the device inside of the box. There is even special place with like I have the magnets for the holder, so I can put it like on the like special place. I want it in the middle, so that each antenna is actually pointing to the device. And yeah, why we have like I didn't tell like why we have like those more antennas. So the idea when the EMC is done, so you are measuring device from all the sides, and when you have like antennas on the multiple peaks, you can actually just connect the device on the other peak, and you can measure if that side of the device will broadcast, like, because we don't get the reflection, so if that side of the device can do. So that's it, and this is the actually probe holder, so I just put the material in the middle, and I also like designed just for blockage like those peaks, and there is also, and I also told you that I designed like this like edge stuff, so that I block the signals inside of the edge. This is that special RF material, so we can test that outside. I also have like new amplifiers, so we need to test it if this is, it is much better than the one I have used for the measurement. So because it has like on all frequencies, it amplifies similar. So we can also check that outside. And this is actually the board, the antenna board that we designed, and we hope it will work. One of the antenna is currently soldered, so I need to solder others, but we can already test. So that's it.